Hello, and welcome to the next video on this channel. I would say go Sox, but they're literally not playing because they sucked this year. What the heck?
Hectogon.
So this video is going to be a continuation of the laws of the trigonometric functions that I did not too long ago. I'm going to finally prove the lovely little formula for the area of a triangle known as Heron's formula. It's a very trivial formula to know or memorize, but the proof of it is actually quite nice and utilizes a lot of things that we've proven on this channel before. That's all the introduction I need for this video. A couple other things. Currently I'm going through my abstract algebra text to try and relearn some of that stuff, and alright, I was a little incorrect. It is pretty interesting actually. It's quite a lovely little subject. So more on that in the future. Also, I had a secondary Instagram account at one point where I would post my record collection and books that I'm reading, but I've now changed it to the official Instagram page for this YouTube channel. It's just called What the Hectogon, just like the channel name, but with no spaces and no question mark at the end. I'm still going to post my record collection, as you can see in the background, and books that I'm reading. What did I just get finished reading? So currently, like I said, in the math world, I'm doing my abstract algebra textbooks. That counts as reading, I guess. I just finished reading Hitch 22 by Christopher Hitchens, and I'm a bit of the way through The Comet Sweeper by Claire Brock, about William Herschel's sister. William Herschel discovered Uranus, and from that, Neptune was discovered after that, but his sister discovered 8 different comets in her lifetime in the 17 and 1800s. She was a brilliant astronomer, and I'm really loving this book, so I would recommend either of these wonderful pieces of nonfiction biographical works. So go follow the Instagram page at What the Hectogon, and remember, if you have any questions, you can email me at the misspelled What the Hectagon, because when I first made the email I didn't actually know how hectagon was spelled. I guess I could have just looked at the word hectometer or hectogram, but I didn't, and so it's misspelled, and Google won't let me change it for some stupid reason. So the email is misspelled, everything else is correctly spelled, and the email is spelled What the Hectagon, as opposed to the correctly spelled What the Hectogon. So follow me on Instagram and email me if you have any questions. Let's do this. So today we're covering Heron's formula for the area of a triangle. Now, if we are given an arbitrary triangle with side lengths A, B, and C, it is the case that given this other value, S, which in previous videos we've called it the semi-perimeter, which is what S stands for, and by semi-perimeter it means the length around the triangle divided by 2. So A plus B plus C all over 2. So given this amount, the area of any triangle with side lengths A, B, and C is equal to, we'll call the area capital A, this is equal to the square root of the semi-perimeter times the semi-perimeter minus the side length A times the semi-perimeter minus the side length B times the semi-perimeter minus the side length C. So this is Heron's formula, and we're going to set out to prove that this is actually true today. This works for any triangle. It doesn't matter what A, B, and C are. If you know the 3 side lengths, you can tell me the area of the triangle. It's not difficult, but let's prove it, okay? So to start off with, we need to recall the law of cosines. I proved this in my video on the law of cosines, and so if we have another arbitrary triangle with side lengths A, B, and C, and the angle between A and B, we'll call it theta, then the law of cosines simply states that C squared is equal to A squared plus B squared minus 2 times A times B times the cosine of that angle theta. Right? And so this is essentially just a generalization of the Pythagorean Theorem, which we've covered plenty on this channel. And you can see that it has to be because if theta is 90 degrees, or pi over 2 radians, then the cosine of that is 0, and this term goes away. And you're left with the very, very familiar Pythagorean theorem that states that A squared plus B squared equals C squared. So this is like a general Pythagorean theorem. And we're going to need this for proving Heron's formula. So what we're going to do is we're actually going to solve for this cosine of theta term. And I'm not going to go through all the algebra, it's not very difficult. You will find that the cosine of theta is equal to A squared plus B squared minus C squared all over 2AB. Okay? If you solve for the cosine of theta, that's what you will end up with. So that's step 1, we have the cosine of theta. Step 2 is we need to recall one of the Pythagorean identities that we learned when we did the unit circle, which was that sine of any angle theta all squared plus cosine of that same angle squared is always equal to 1, which means we can solve for sine of theta because sine of theta is therefore equal to the square root of 1 minus cosine squared of theta. Right? And this is not sine of theta squared, it's sine of theta all squared, the whole term. And this is solving for sine of theta. And this is very good because look what we can do. We can actually plug this into there, which is very, very helpful, and we will see that we're going to do that. And now we're going to use the law of sines to come up with a way to write the area of this triangle. So we have cosine of theta solved for from the law of cosines, and we have a representation of sine of theta in terms of cosine of theta. So those are the two things we need first. And the last thing we need is to rewrite this triangle a little bit. We're going to tilt it on its side, so we end up with this. So this is theta, this is A, this is B, and this is C, right? And we know that the area of the triangle is equal to 1/2 times the base times the height. And so given the law of sines, we know from the law of sines that the area of this triangle has to be equal to 1/2 times the base A times the height, which is B times the sine of theta, right? B times the sine of theta. So we have all three pieces that we need to show. We have that cosine of theta from the law of cosines, given a triangle, is equal to the side length a squared plus b squared minus c squared all over 2 times a times b. You can pretty easily solve for it just by using the law of cosines. We have from the Pythagorean identity that sine of theta is equal to the square root of the quantity 1 minus cosine squared of theta. And we have from the law of sines that the area of this triangle, these are supposed to be the same triangle by the way, I just turned it so that a is on the base, we get that the area is 1/2 times a times b times the sine of the angle between them. Okay? So these are all the tools that we need, and now we're going to use them to prove Heron's formula for the area of triangles. So I'm going to start with this. So we have first that the area of the triangle is equal to 1/2 times a times b times the sine of the angle between them, which we called theta. We can replace sine of theta with the representation that we have of cosine, right? So we have it as 1/2 times a times b times the square root of 1 minus cosine squared of theta. But what was cosine? Cosine was that weird representation that we had from the law of cosines. So this is actually equal to this 1/2 times a times b times the square root, and this is going to be big, 1 minus, and what was that representation of cosine? It was a squared plus b squared minus c squared over 2ab all squared. That's quite a mouthful. Remember, this was cosine of theta as solved for from the law of cosines. What I'm going to do is I'm going to distribute this square into the numerator, so we end up with just the numerator squared, but I also have to square the denominator, so this is going to become 4a squared b squared. 4a squared b squared. But then look what happens. This 1 can be combined with this if I just write it as 4a squared b squared divided by 4a squared b squared, right? So I can write this 1, I can add it into the fraction by simply adding 4a squared b squared to the numerator, because 4a squared b squared divided by 4a squared b squared is 1, right? So I hope that's clear. All I did was change that 1 into this divided by itself, which is still 1. But notice what happens. If we're dividing by 4a squared b squared, this is the same thing as 1/2 times a times b times the square root of the numerator, which is 4a squared b squared plus a squared plus b squared minus c squared all squared, divided by the square root of this thing, right? Because the square root of the denominator, I can just write it as the denominator of the new fraction. And the square root of 4 is 2, the square root of a squared is a, and the square root of b squared is b. And that's actually pretty nice, because now this and these will actually cancel quite nicely. 1/2 times 1/2 is 1/4. A divided by a is 1, b divided by b is 1, and so we're left with just this radical, which is the square root of 4a squared b squared plus, oh, my mistake, it should have been a minus, I apologize. So it was 1 minus cosine squared of theta. We replaced cosine with that representation we got from the law of cosines, and then I turned the 1 into 4a squared b squared over 4a squared b squared, and I accidentally added it when I meant to subtract it. So those pluses should be minuses. Sorry about that. So that should be minus, and we get a squared plus b squared minus c squared all squared, right? So that's pretty good so far. So this is still just the area of the triangle, right? And we've got this so far. What's really nice about this, though, is that this is a perfect square, and so is this, which means we can employ the difference of squares, right? Because we have a square minus another square. So we can write this as 1/4 times the square root of this plus the square root of that. So we get 2ab plus a squared plus b squared minus c squared times this minus that. So 2ab minus a squared minus b squared plus c squared. But we could just write it as minus that whole thing. So minus a squared plus b squared minus c squared. Okay, I hope that's clear. All we did was difference of squares, right? It's something squared minus another thing squared is the first thing plus the second thing times the first thing minus the second thing, right? So those can be in parentheses like that. I hope that's clear to everybody what I just did. And now what we're going to do is we're going to combine these in a very nice way. Because look what happens. We can rearrange these terms, and so we get 1 over 4 times the square root of a squared plus 2ab plus b squared minus c squared times negative c squared is positive c squared minus a squared. And I'm going to put these in parentheses. So minus a squared. I'm going to factor a negative out of this as well. So we're going to get minus 2ab, which makes the plus 2ab still there. So we're going to get minus 2ab in there. Notice this negative will cancel with that negative, and we'll get the positive 2ab back, so it makes perfect sense. And this negative times that plus b squared is going to go right there, so we get the positive b squared. And now, we actually have another two cases of differences of squares, because what is a squared plus 2ab plus b squared? This is actually, we can rewrite this one more time, we get the square root of a plus b all squared. So we get a plus b squared minus c squared. And here we have c squared minus, and what's a minus 2ab plus b squared? That's a minus b all squared. So we have minus a minus b all squared. So now we have like a double difference of squares going on here. And so now that we've gotten to this step, and again, this is all still just the area of the triangle. Feel free to follow through these steps again if it's confusing to you. All I'm doing is doing algebraic manipulations. And now we have another two differences of squares. So I'm going to rewrite this one at the top of the board, and I'm just going to erase everything else. So if you haven't followed up till now, just rewatch what I've done so far. I made an error before and I corrected it in the process of the video, so I apologize for that. So we're going to take a look at this now and move on from this step. So this is where we're at now, right? The area of the triangle, which I denoted by capital A, is given by 1/4 times the square root, and the a, b, and c are all the side lengths of the triangle, so it's 1/4 times the square root of the quantity a plus b all squared minus c squared times c squared minus a minus b all squared. Okay, so again, if it's not clear how I got to there, just rewatch the steps I did before. We're just going to continue from here because look what we have. We have two more differences of squares. So again, I can keep rewriting this. So we can write it as the square root of a product of four different things now. So it's going to be this thing minus that thing. So we get a plus b minus c times this thing plus that thing. So a plus b plus c. And then it's this thing minus that thing. So we get c minus a plus b. And we get c plus that thing times c plus a minus b. Right? Very, very good. And now what we're going to do is we're going to divide every single one of these things by 2. But if I divide every single thing by 2, that means I'm dividing by 2 here, 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 and here. So dividing by 2 4 times is the same as dividing by 16, right? But because we're under the square root, then dividing by 16 under a square root is the same as dividing by 4 on the outside, right? But we already have that, right? It's already here. So 1 over 4 on the outside of a radical is the exact same thing as 1 over 16 under the radical, because the square root of 1/16 is 1/4. So all I did was take that 1/4, square it, and put it under the radical, because those are the same thing. But if I'm dividing by 16, that means I'm dividing by 2, and then 2, and then 2, and then 2 again, right? Because 16 is 2 to the 4th power. So what I can do instead of dividing by 16 is just divide each individual one of these terms by 2. This product of 1/2, 1/2, 1/2, and 1/2 is the same as 1/16. And now it's about to become pretty clear where this is going to go. Because what I'm going to do is I'm going to rewrite this slightly. I'm going to take this term and leave that right there. So that gives us a plus b plus c over 2. And that's going to stay right there. That should look familiar because this is the semi-perimeter, right? It's the sum of all three of the sides divided by 2. So it's the perimeter cut in half, which is the semi-perimeter. I'm going to rewrite this term as a plus b plus c. But if I'm adding c, I have to somehow still get minus c. So if I'm adding 1c, I have to subtract 2 c's so that I still end up with minus c. So minus 2c all over 2. And this one is going to be b plus c minus a. So if I still want it to be a plus b plus c, I have to then subtract 2a, right? A plus b plus c minus 2a all over 2. I still get b plus c plus a minus 2a gives minus a all over 2. So that still works. And then the last term is much the same. It's going to be a plus b plus c minus 2b, because there's a minus b, so I've got to cancel that out and still get minus b in the top. So it's a plus b plus c minus 2b all over 2. And again, this is still the area of the same triangle, but look what happens now. Look how I can rewrite this. I can rewrite this as the square root of a plus b plus c over 2 times a plus b plus c over 2. What's minus 2c over 2? That's just the same thing as minus c, right? Because negative 2c over 2, the 2's cancel, and I just get minus c. So I can write this as minus c. And this one is the same way. It's a plus b plus c over 2. And what's minus 2a divided by 2? That's the same as minus a, because the negative 2 and the 2 cancel, and we just get minus a. And the last term works the same way. We're going to get a plus b plus c over 2 minus 2b over 2, which is the same as minus b. And if you'll notice, that's the semi-perimeter, that's the semi-perimeter, that's the semi-perimeter, and that is the semi-perimeter. And it follows all of the subtractions like I said it would. So I'm going to now rewrite them in this order. I'm going to write this one, then this one, then this one, then this one. Because look what this is. This is the semi-perimeter S times the semi-perimeter minus A times the semi-perimeter minus B times the semi-perimeter minus C. Exactly like I said it would be. And that, my friends, is the proof of Heron's formula for the area of a triangle. The area of a triangle is given by the square root of half the distance around the triangle times half the distance minus the side length A times half the distance minus the second side length B times half the distance minus the third side length C. A beautiful, beautiful formula. And all we had to do was use the law of cosines, the law of sines, and Pythagorean identities, all of which we have proven in previous videos. So if you're not sure about that, you can go back and watch those. Now that we've proven Heron's formula, I want to give a sort of corollary to that I'm not going to prove, but I need to explain a bit of a concept first. I need to explain the idea of cyclic polygons. Now, if you recall the sort of aside that I did in the cotangents video about the law of sines, that proved that the law of sines had to do with the circumradius, or the circumcircle that circumscribes a triangle. That's a terrible circle, but the idea gets across. There is a unique circle that touches every single vertex of a triangle. For every single triangle, there is one circle that does it. And this is what defines a cyclic polygon. A cyclic polygon is a polygon whose vertices define a unique circle, or define a circle in general. Every triangle is cyclic because every triangle has a unique circumcircle. Not every other kind of polygon is cyclic. You can imagine that if I added a fourth side here, like this point here, this shape still touches all three of these parts of the circle, but this vertex is sitting inside the circle. And this is, right here, a counterexample to the question, is every quadrilateral or four-sided polygon a cyclic polygon? It's not, because this point is not touching this circle. The cool thing is that Heron's formula is actually sort of a specialized version of the area formula. So we have that the area of this triangle is equal to the square root of the semi-perimeter times the semi-perimeter minus one side length A times the semi-perimeter minus the other side length B times the semi-perimeter minus the other side length C. But notice, this S is just kind of oddly on its own. This semi-perimeter is sort of all by itself. Because what is actually really going on here is a cyclic triangle, which is all triangles are cyclic, is in some kind of way like a quadrilateral with one side being equal to 0, right? Like if one side of a quadrilateral is 0, you could imagine that it just goes to a point and we're left with a three-sided shape, or a triangle. So I'm going to rewrite this slightly, because this is a true statement. I can subtract 0 and nothing will happen. S minus 0 is of course still the same as S, right? So this is still a true statement, I'm just subtracting 0. But what if that wasn't 0? What if we did have a quadrilateral, all four vertices actually touched the circumference of a circle? Well, then we could call this fourth side D, and you end up with a very, very special formula that you could rearrange so that it's S minus A, S minus B, S minus C, and S minus D, but multiplication is commutative, and I'm sure that people watching this understand that I can write that in any order. And what you've got here is not Heron's formula, but something called, now let me just make sure I'm spelling this right, Brahmagupta's formula. Brahmagupta's formula. Now, not every quadrilateral is cyclic, or, in other words, not every quadrilateral has all four of its vertices sitting on some circumference of a circle. But those who do, this is how you can find the area. So, in reality, Heron's formula is actually a simpler version of this, where you can imagine that one of the sides of this quadrilateral is actually 0. Right? And s minus 0 is just s, and you end up with a triangle, where the interpretation is that that triangle is actually just a four-sided shape where one of those sides is 0 in length. So you end up with Heron's formula. But if you have a cyclic quadrilateral, which is you have a particular quadrilateral such that all four of its vertices lie on some circle or define a circle, then you can use Brahmagupta's formula, which is a more special version of Heron's formula, but it's used for four-sided polygons instead of three-sided ones. I'm not going to prove this one, I just think it's an interesting aside to state that that lone s that was sitting there wasn't there for no reason. It's actually just like having a quadrilateral where one of the sides was 0 and you just have that lone s on its own. So that's all I wanted to go over in this video. I really enjoy Heron's formula. I think it's a neat little fact. It's not at all intuitive, just looking at it, that that would be the area of a triangle, and all you would need to know are its three sides. But it's very, very cool, and I thought I'd just share Brahmagupta's formula for the area of cyclic quadrilaterals, not any quadrilateral, only cyclic ones, which again, it means that all four of its vertices sit somewhere on the circumference of a circle. It doesn't have to be a specific circle, it just has to be a circle, and that's actually quite a strong assumption to make. So this only holds for cyclic quadrilaterals. Heron's formula holds for cyclic triangles, but all triangles are cyclic, so it holds for all triangles. And I hope that was an interesting little excursion into the world of ancient Greek and ancient Indian geometry. So thank you very much for watching, and I'll see you in the next video.